And now I'm going to quickly introduce Team iCow, starting with our technicians. Our head technician here is Hesbon, um, and being assisted with by Mike. Thank you so much, Team iCow, our able technicians. We also have with us tonight is Beth, customer care assistant, and
hello class. Welcome to today's class, and I hope you will all enjoy. Thank you, James.
thank you so much, Beth, for that. Hesbon, if you can also greet the team.
Hey, hello class. Welcome to Module 2. I hope you're going to enjoy the class.
Thank you, Hesbon, for that. For me, I didn't mention my name at the beginning. My name is James Ebiwat. I am your moderator, iCow Soil Advocacy Program moderator, and we shall interact together all through this session. And don't hesitate if you need clarification for anything, you have a question, please reach out. I'm always available, and we shall going to enjoy together, learn together. And finally, I'm going to introduce Sue, CEO of iCow, and also our iCow Soil Advocacy Program instructor. Let us put our hands together as we invite her to take us through Module 2. Let us clap for Sue. Welcome, Sue.
Thank you, James. Thank you so much. And thank you to everybody who's here. I see you guys on YouTube. Florence, nice to have you with us. There are a few others there. I don't have your names. Do put your names into the chat so that we can interact. Sister Oriel, you didn't receive a message on Canvas. I hear you. We see you. We will correct that. James or Beth will jump in and help you with that. Yesterday, we did a history of soils. We went back 4.5 billion years. And today, I've got three wonderful, two very short and one slightly longer videos that again help to position our thinking and our for this course around soils. We've curated this course very carefully to make sure that we're all, going on a trajectory that helps us get to why we need to be thinking about the microbes and building biocomplete compost for our systems. So today, before, without wasting any more time, I'm going to go straight in and I'm going to share with you the first video. The first video is a video by our friends, and I must say, I really do appreciate the team from Kiss the Ground. I don't know if any of you have seen Kiss the Ground, the movie, or any of the information that they've put out there. They were part of the people that inspired me to do our soil advocacy course. And they enabled us to actually use their content from this very, very lovely movie called The Soil Story. So we always say great kudos to the Kiss the Ground team. They really are blazing a trail in this area of soil regenerative agriculture. And we're going to go on and watch this short video, take some notes, and off we go.
If you're like most people, you're probably feeling a little hopeless about climate change and the damage we've done to our planet. Well, now there's a new way to look at climate change and how to deal with it that might just turn that hopelessness into hope. Climate change, as we know, is all about too much carbon in our atmosphere. But carbon is not our enemy. It's the building block of life. Everything alive is made of it, even us. The problem and the solution are simply a matter of balance. Let's step back and look at the 5 pools where carbon is stored on planet Earth. Starting about 500 million years ago, when plants first appeared on land, carbon began to cycle in an amazing balance between these pools, a balance that allowed for life as we know it to evolve. Then one life form, that would be us, figured out how to extract carbon from the fossil pool, which was pretty much a timeout zone for carbon. We've been burning it for energy, putting into play, and disrupting that balance. The way we manage land and do agriculture is moving even more carbon into the atmosphere. Specifically, we've moved 880 billion tons of carbon dioxide into the atmosphere, which is heating up the planet and destabilizing our climate. The oceans have absorbed a lot of this excess carbon, throwing off the ocean's balance, resulting in ocean acidification and accelerating a mass extinction of sea life. So in order to save life as we know it, of course we need to stop burning fossil carbon. The big question is, where do we put this excess carbon to get the cycle back in balance? The good news is that the answer is literally right under our feet. It's the soil. Plants, using sunlight and water, naturally perform photosynthesis. They pull carbon in from the air and turn it into carbohydrates, sugars. Then they pump some of these sugars down through the roots to feed microorganisms who use that carbon to build healthy soil. Voila, carbon moved. The plants pump it in, and the soil stores it. Nature's living technology is amazing. Scientists have recently discovered that applying a thin layer of compost can help regenerate healthy soil, setting up an ongoing feedback loop that brings more and more carbon into the soil each year. Together with other regenerative practices like not tilling the soil, planting trees and cover crops, and planned grazing, we can build and retain billions of tons of soil carbon. This is carbon farming. This is regenerative agriculture. Unlike more carbon in the atmosphere, more carbon in the ground is good for us. It makes healthy soil, which is nutrient-rich and full of life and holds way more water. This means more nutritious food and crops that are more resilient in the face of drought. That's good news for farmers, families, and everyone who eats. Remember this: the way we grow our food, fiber, and fuel either puts carbon up into our atmosphere or pulls it down into the ground. The regeneration of soil is the task of our generation. Our health, the health of our soils, and the health of our planet are one and the same.
Every time I see that, it just blows me away. Can I see everybody give a bigger heart reaction, if you enjoyed that, to the Kiss the Ground team who made that video? It really is so concise and really does just, for me, it just underpins, well, life as we know it. Does anybody have any comment that they would like to make? Any question, any comment? What we will do after these few videos that I'm showing you is have a chat. And the chat is, it's not me. I'm not going to over chat you. The chat is with you. Charles, thank you for putting your hand up there. You've got this. So let's give Charles a microphone. You'll see that you'll get the option to unmute yourself, Charles. Put your camera on and come on down and let's have a chat.
Yes, thank you so much, Sue, and thanks to the Kiss the Ground team that made this marvelous video. Actually, I'll be happy to have a link and keep watching over and over again. Yeah, so yeah, but one thing comes to mind. Yeah, you see, we've been in the soil health, carbon sequestration, climate mitigation, climate adaptation debate for quite a while. And I'll take an example of Africa. They say Africa contribute less than 4% of the global greenhouse gas emission. And so does it really pay off for us to invest heavily in mitigation, climate mitigation, carbon sequestration, through all practices, agroforestry, tree planting, building the soil sponge, and whatever we need to do to remove greenhouse gases, notably carbon from the atmosphere. Is it our issue as Africa, now that we only contribute less than 4% of the global greenhouse gas emissions, and China, Russia, the US, and those other big economies are the ones, pushing these greenhouse gases in the atmosphere. So like they darten the room and it's our role to clean the house, something like that. So there's that debate. Can we focus on adaptation more than mitigation? So I don't know what your comment is on that.
Charles, what country are you from?
I am from Uganda.
You're from Uganda. Great, great. And please, when we do speak, let's all mention our names and where we're from, because I just think it's so lovely that that gives us that, that real continental view of how this course reaches out to so many people from different places. You asked, is it our issue? The right answer is the planet, irrespective of who is making up the mess is becoming everybody's issue. You asked, should we be looking at mitigation as opposed to adaptation, or just adaptation? And I'm going to ask you for those that don't know in the audience, do you want to tell us what is that difference there, Charles? What is the difference between climate mitigation and adaptation? What are the different things people will do? What are the different outcomes? What are the different costs? Go ahead there, Charles.
Yes, thank you so much. Yeah, so briefly, mitigation is to do with the cleaning job. Like, because the main cause of the global warming, the increase in temperature, is the emission of the greenhouse gases that go and tamper with the ozone layer, and then we have the earth warming up and temperatures going up, and then climate change is pronounced to be here. So by mitigation, we are like, can we can we clean up the atmosphere by removing the greenhouse gases largely? And this is the sequestration, the carbon sequestration.
Mm-hmm. Oh, we've lost you a little bit. Are you still there? Charles seems to have fallen off for a minute. We can't hear him. So we're going to go to the next, was it somebody else had their hand up? Okay, there you go, Zandile. Why don't you jump in? And if Charles manages to come back, we'll continue with him. Maybe you want to add on there. What do you understand by, we've understood that mitigation as being part of the cleanup job. Nightingale has said it's preventing or reducing emissions. Zandile, let's hear what you have to say. Tell us where you're from. And then also, if you can fill in that last part of the question that I asked Charles, which is about adaptation. What is adaptation?
Hello everyone, my name is Zandi Defraz. I'm from the country South Africa. No, I just wanted to ask something. I wanted just to ask a question. I want to know if carbon farming is the same as smart farming.
Okay. I think that any farming where we sequester carbon, with the aim of not just sequestering carbon as carbon and chunking it in the ground, which is what some people are doing when we start speaking of things like using the use of biochar in agriculture, etc. But sequestering carbon through the natural systems, through plants and through soil microbes is smart farming. It's the smartest thing anyone can be doing. Charles may not be here yet. I'm hoping he manages to come back because I do want us to touch on what he means by adaptation. The reality is this, in my mind, is the climate catastrophes that are happening, wherever the blame lies, they will hurt everyone, and they're hurting the global south the most. By my opinion, adaptation is absolutely necessary, but adaptation will not stop what's happening. We need to do both together, the way I feel. It should not come at the cost to the developing countries or the countries that have not been those that are the biggest emitters. And that's what part of the COP conversations are. And, you know, part of all the climate conversations that are going on are about this. The climate fund is supposed to go. There's a lot of climate carbon trading and different trading mechanisms of trading carbon, which are ongoing as well, which I don't believe in. But on this note, let's use this as a segue into our next video, which is actually going to show us what that carbon dioxide actually looks like in the atmosphere. This video is a year in the life of Earth's O2 by one of the NASA satellites. And what's very interesting about it, it is a year, it is 206, and they have got some that are slightly more recent. But even back then, it gives you an impression of what was happening and how carbon dioxide cycles in the air. It's much worse now, and some of you can Google the NASA CO2 satellites and some of the later imagery, but this for me is a great video that we're sharing in class that actually shows us what it was like then. Very profound video. I hope you enjoy it, and we'll ask questions and hopefully have Charles come back on about adaptation after this. So off we go.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the Northern Hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia. Notice how the gas doesn't stay in one place. The dispersion of carbon dioxide is controlled by the large-scale weather patterns within the global circulation. During spring and summer in the Northern Hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors fade. Meanwhile, in the Southern Hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS-5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
Now that was a visualization of, a couple of things that I think very much connect with our conversation before this with Charles and the video of the soil story. The plants drawing down the carbon dioxide. But the emissions that we're putting up, 50% of them are staying up year on year on year on year, and that was 2006. How much is still up there? According to the soil story, 880 billion tons of carbon dioxide, and the soil story video was made a couple of years ago, so there's even more than that now. Does anybody have any comments that they'd like to make about that video? Was it eye-opening for you? If you felt it was eye-opening, you can just make a comment by showing a thumbs up or something, so that I can get an impression how you've all felt with that particular video. For me, it's always been, it scares me when I look at things like that. Further to your discussion that we're having before, Charles, when we look at what emissions are we emitting? So if we look at, first of all, we're all emitting something. And as humanity is growing in terms of numbers, population growth, we're all emitting more of those things. So collectively, the emissions from the global south, we're looking at those carbon monoxide emissions. The global north, we're looking at carbon dioxide emissions, of course, much more. But what I want us to take away from there is what happened during spring and summer, and how it was very clear in that imagery that the carbon dioxide got sucked back down. And it was because people were planting. Those are the seasons that the farmers are out there planting. Those are the seasons that there's the photosynthesis, that the plants are planting. But as you go along in this course and you remember this video and you remember the previous video you watched, it isn't just the plants. It isn't just any plants. The plants that plants will photosynthesize and plants will die and plants will decompose. But if we want that sequestration to happen down into the depths of the soil and build those soils, which will help in exchange to provide plants with nutrients, etc., we need the microbiome to be working. Because if we look at it from the plants are sucking down that carbon dioxide, where is the demand coming from beyond their roots or within their roots? They don't need to do too much work in terms of the liquid carbon pathway if the soil microbiome doesn't exist. And there will be no carbon sequestration if the soil microbiome doesn't exist, because it is the microbes that lock that carbon in. So what I'm hoping we'll get that connection. And this course will, as we go on, will further that. We have another very, very interesting video that talks exactly about that and about that carbon liquid pathway, which I'm going to play next. We're going to take 2 questions from the audience, from you students now. Vivian, thank you. You put your hand up first. Let's give Vivian the microphone and camera, and let's talk about it. Come on down, Vivian.
Hello.
Come
Can
down.
you hear me?
Yeah, but you're up there. Come down.
Where am I?
There we go. Now you're down. Okay.
Okay. Thank you so much for that video is such an amazing and helpful visualization of what we're talking about in terms of the science. I wanted to know if you are able to comment a bit more on this. You mentioned it very briefly about biochar and how you don't believe that that's necessarily a very effective way of sequestering carbon, because there's been so much talk in some of the spaces that I've been in, and I've also wondered, but what I'm hearing you say is that it's actually much more effective to put carbon back in the soil the natural way through the microbiome. Can you explain what the value of biochar is, if there is one? Just because it just seemed to me like there's a lot of hype around it, and I haven't always quite understood the place that maybe there is a lot of value.
Great, thanks for that, Vivian. So there's a lot of information out there about biochar. So biochar is either the pyrolysis of high carbon matter like wood or crop residues or other things like that. And it can be used as it becomes very alkaline. The biochar is very alkaline. Biochar is purported to be very good for soils because it apparently helps soils hold water. It helps change the acidity of soils. If your soils are very acidic, it can actually make your soils, bring your soils down from acidity. If we face the problems and really face the problems head on as to why our soils are acidic, so that there are two parts of this story that I'm very passionate about. One is if our soils are acidic, and we think that just by putting in something alkaline is going to change that, whether it is lime or whether it is biochar, we've not solved the problem. What has driven our soils to being acidic? Because if we've not solved the underlying problem, they will resort to being acidic again in the future. And the reason our soils are acidic is because they're compact. Compact means that the soil particles have the soil structure and the soil systems that are built by the soil microbes doesn't exist. They've failed. They're no longer there, and the soil particles have fallen on each other. There is no air in the soils. The soils have become like concrete, and plants find it increasingly difficult to even get their roots into soils like that. And that's where we end up with soils that will wash away, soils that will blow away, and soils that are not productive for our systems. If we think about microbes, and we think that the food for microbes is organic material and the carbon that is being brought down, the liquid exudates that are being brought down from the roots. And we know that what we need to solve these problems are microbes, then why are we burning? Why are we pyrolysizing stuff that can be turned into massive production of microbes that we can bring back and inoculate our soils with? That's the second part for me. The other part is when there is also scientific papers that have been written on biochar and how, yes, it does take a very long time. The theory is it doesn't break down very quickly in the soils, and therefore it's sequestered and can be sequestered for thousands of years and stay in the soil for thousands of years. There's also information that talks about how biochar is, in the beginning, it deters microbes because it is so alkaline. So it does the reverse of what we want to the existing biome in the soil. When we simplify that to ash and what organic farmers use wood ash for, they use it to deter pests. They use it to, prevent pests on their crop. The reason the pests are there, they're there as messengers that there's something wrong with the soil. And we're using that burnt ash as a repellent. When we bring that down to, what then happens when we put this into the soil systems and we're trying to grow life in the soils, I think it's quite evident that if there were a way of producing microbes and then we continue putting in biochar that does the opposite and repels them, why would we be doing that? But each one to their own. Everybody's soil is different and everybody's views around biochar are different. These are my personal views. I feel very passionately about keeping the soil microbiome alive by feeding the biome with materials and not putting things in like biochar that might change the acidity and maybe send them or not help them prosper as much as we'd like. We don't have another hand up. I can see that there were, and that was quite a long discussion. Thank you for that, Vivian. I can see that there are some people commenting on it in the chat there. I do want to just go back to the adaptation, and we've got Nightingale saying basically anticipating these effects of climate change, taking steps to reduce or prevent the effects. So here's the thing, we can try to produce and prevent the effects, but if we don't help to stop, it's a little bit like the whole story of sick plants and just treating them symptomatically to get something on our plate to eat without solving the actual cause of the problems. So I think that mitigation and adaptation go hand in hand. I think that it is absolutely horrendous that the global south and also those low-lying nations are the first to suffer from climate change. I feel it is horrendous that climate and carbon and all the carbon solutions have now become more of a geopolitical debate than anything else. But I have hope that individuals like you who are taking these classes and become soil advocates, go out and advocate to your communities, to the farmers, to the people around you, that we can play our part in understanding, and whatever word we give it, we do play our part, because the blame game and the money game is not going to stop these colossal impacts of climate change. We're seeing it, floods. We can try and adapt for floods, but I think mitigation and adaptation hand in hand. We need to have resilience in our plants to begin with. We need our plants to be as strong as they can possibly be from an immunological perspective, and they need the microbiome to get to that. They need to be able to withstand the pressures of too much drought, too much water. They need to have the root networks to manage to build the soils, and the soils need to be able to absorb that water and absorb that water when it's coming down now hard and fast, because our rainy seasons are changing as well. So I hope that also helps a little bit in the new thinking and the relearning. Now we're going to go to the final video. And she is one of my favorite gurus in this place of soils. I want you to listen very carefully. And please, if you've got pen and paper at hand, take notes. And take notes of this specific speaker and Google everything you can on her. She's Dr. Christine Jones. She's a soil ecologist in Australia. And she's going to be talking. She's talking in this video in the US about building new topsoil through the liquid carbon pathway for long-term productivity and profit.
It's a great honour to be here, and I'm looking forward to discussing things further with people during the breaks. I've got 40 minutes this morning, so I've been told, to explain the meaning of life, I guess, in 5 words or less. I'm going to be rushing through this fairly quickly. So if you would, want to ask questions, we won't really have time this morning, but this afternoon I'm hoping to allow a little bit of time in my talk to be able to field questions, or as I said, you can chat to me during the breaks. This is, some of you may have seen this, Darren Corman's work on Canadian net farm income. I realise this is a different country, but I think you'll agree that the statistics are fairly similar to what's happening here in the United States. I don't have a pointer either, sorry. Unless, no, that's not one. Okay, I do have those things in my bag. I should have brought them up here. But anyway, if you have a look, this goes from 1926 to 2016, this 80-year period here. If you look right up to about 1970, you'll see the blue line, or the blue area, is actually the gross revenue earned from agricultural production. So it goes up and down depending on the seasons, on commodity prices and all that sort of thing. We're aware of all these changes that happen to gross revenue over time. The green line is net farm income. It's your net revenue back on the farm. And you'll see that up to about 1970, when seasons were good and commodity prices were good and gross revenue went up, net farm income went up as well, and then when things went down, net farm income went down. And that's the kind of relationship between gross and net that we would like to see. But then after about 1970, those two lines start going in different directions. Gross farm income, or gross revenue, continued to go up, and it is still going up. But the green line, your net farm income, has been going down. And in fact, in 2006, which I figure was probably the same thing here, it's in the red because of the low corn prices in that year. So what is going on? Why are these two lines separating and going in different directions? Well, if we have a look in a little more detail at this data, and I have a link to this paper if anyone would like it, it's very, very insightful. In the 32-year period from 1985 to 2016, that is agribusiness, like the input suppliers, the people who supply you with your seeds and your fertilisers and your tractors, and the lenders and all those, the service providers, received $1.32 trillion of the $1.35 trillion of revenue earned through agricultural production. In other words, 98%. So 98% of what was earned in the agricultural industry went to input providers. And today the majority of Canadian farmers are supported by off-farm income, taxpayer-funded support schemes, asset sales and borrowed money. Does that sound familiar? Well, and farm debt in Canada is at a record high, just under $100 billion, and farm debt in the USA is also at a record high. And we down under in Australia, we can't point the finger at what you guys are doing up here, because we have exactly the same trend happening in Australia. So that figure there, the green line is our revenue and or the gross value of farm production, and the red line is debt. So debt is overtaking our farm production. And if we just look in something that I'm a little bit more familiar with, we grow a lot of wheat in Australia, and our average wheat yield doubled between 1980 and 2000, and in that same period, farmers' profits halved. So I'm not pointing the finger at the United States by any means. Now, we're repeatedly told that we need to produce more to get out of this mess, but it's actually not about maximising yield. So it's not about maximising yield, it's actually about optimising profit. And we have to regenerate the resource base, and we want to be producing nourishing food. So I just want to dwell on that for a moment. We're linking soil health and human health. Lloyd Noble, who was the founder of the Noble Foundation, said that no civilization has outlived the usefulness of its soils. Well, I want to add to that no civilization has outlived the health of its citizens. And if you think that's a grand statement, you really need to look at the health situation here in the United States. At the moment, United States citizens spend twice as much on health care than people in any other country in the world, but your health and life expectancy actually rates 17th on the list of other countries. Cardiovascular disease, cancer and Alzheimer's are the three leading causes of death in this country, and all are nutritionally related. All can be reversed with a change in the diet. 46% of children in the United States now suffer some kind of chronic disease, and those of you who have children or grandchildren will understand exactly what I'm talking about. The childhood illnesses are scary, and they are increasing exponentially. They're not infectious diseases. They're all to do with the food. There's been a dramatic increase in the incidence of over 80 autoimmune disorders in recent years. That's where the body's immunity is not functioning effectively. They currently affect 1 in 6 Americans, and the numbers are growing daily. It's going to be, 1 in 5, 1 in 4, 1 in 3, 1 in 2 very, very quickly. So what are autoimmune diseases? They're non-infectious diseases that include things like diabetes, cancer, autism, Alzheimer's, dementia, lupus, multiple sclerosis, inflammatory bowel disease, rheumatoid arthritis, etc., etc. They're all autoimmune. They're all the body dysfunction within the body. Most of these, if not all of them, can be cured with fecal transplants, which indicates that it's something out of balance in the gut microbiome. They're not infectious diseases. They cost the United States $1.1 trillion a year, but that's just looking at it from an economic perspective. They cost a huge amount in heartache and grieving and emotional upsets within families, especially when these diseases occur in children. So in the early 1900s, Professor William Albrecht said that the loss of human and animal health can be related directly to the soil. That was over 100 years ago. The situation has deteriorated even further in the ensuing 100 years. And given the poor health of our soils, which I think most of you will agree, it's hardly surprising that more Americans are dying from a poor diet than any other factor, because you are what you eat. Now, part of the problem is poor food choices, but even those trying to eat good food are not getting the minerals and trace elements that they need. So agriculture is supposedly about food. I realise that in this country a lot of corn, for example, goes into other avenues like ethanol production, but basically we've always thought of farming as being a food production system, and there is something fundamentally wrong with that food, because the nutritional value of today's food is lower than at any point in history. Despite all the technology that we have, we are producing food that really doesn't have the minerals and trace elements in it that it should. We'd have to eat twice as much meat, 3 times as much fruit, and 4 to 5 times as many vegetables just to get the same amount of minerals as would have been available in those same foods in 1940. I have lots of data on that I'm not going to go through this morning because I have a short amount of time, but you will find it on my website, and it's all published in peer-reviewed international scientific journals. So what has been the effect of this mineral depletion on the plants themselves? Well, we're seeing increased plant susceptibility to pests and diseases, which in turn requires the application of insecticides and fungicides that absolutely would not be necessary if we had healthy plants. This reduces farmers' profits, and it's also adding unnecessary chemicals to the food chain, which is part of the problem that we're seeing with our autoimmune disorders. So just to go back to that figure again and look at that really large blue area, it's only farmers that are suffering as a result of this. Agribusiness in general is doing very well, thank you very much. So farmers are spending more and more on inputs, but the situation keeps getting worse and worse. So the official explanation for this lack of nutrient density in our food is the dilution effect. People will tell you, well, yield has increased. Over the decades, yields of various crops have definitely increased, so therefore mineral levels theoretically fall. If you produce twice as much, we're told, then it will have half the amount in it. But we don't actually see that in crops grown in biologically active soils. We see the opposite. There are farmers around the world who are producing more. Their yields are high, their productivity is great, their resilience is fantastic. In lower rainfall or higher rainfall years, they're managing better than some of the other farmers. And then the food that they're producing is a very high nutrient density as well as being high yielding. Some of our farmers in Australia are now procuring markets, particularly in Asia, for nutrient dense food, which is being segregated. It's actually being kept now stored on farm so that it doesn't go into bulk storage and shipped directly to Asia, and they're prepared to pay a premium for that food. They're also paying a premium for food that doesn't contain nitrate, so grains that don't contain nitrate. And why, you would think, are they picking on nitrate? Like, why not be looking at insecticides, fungicides, glyphosate, whatever, the things that you would have imagined would have been the issue? And it's because the nitrate content of the grain is directly related to all of those other factors. If farmers can grow high mineral, well, they can't grow high mineral grain unless they're not using nitrogen fertiliser, so they have to use something else, a biostimulant, which I'll talk about later this afternoon. And those grains that don't have nitrate in them also don't have insecticides and fungicides. etc., because there's no need to apply them. The plant is able to defend itself. So people are now becoming interested in eating that nutrient-dense food because that is the solution to the autoimmune disorders that we're seeing across the world, not just in the United States. So dilution is not the cause, soil depletion is not the cause. The soil test will show you that in total those minerals and trace elements are still in the soil, but they're no longer in the plants. For some reason, plants are no longer able to acquire the minerals and trace elements that they need, even though they are there in the soil. So why is that? If we had time today, we could explore that and have a good discussion about what the reasons for that might be. But to answer that question in a short amount of time, we first have to ask several others, and that is, well, what is soil? Really, what is that stuff that you're using to produce this food, and by what processes does it form? Because when we understand what soil is and how it forms, then we can see where we've gone down the wrong track and how we may be able to reverse that, so that we can have the kind of nutrient density in our food that we would like to see. We can start restoring soil health in terms of its carbon content and its soil structure, and we can grow crops that are going to be far more resilient in the face of the climatic extremes that we're now facing, and also be more resistant to pests and diseases, which is what we want in farming, because that means when we grow those kinds of crops that our input costs will go down, and we can start having a green line that very closely follows that blue line. So what is soil, and where does it sit in the hierarchy of life? Well, how often have you heard the phrase, the soil is the foundation of everything? It's probably said quite often at these kinds of conferences. Certainly if you go to a soil science symposium, just about everybody will be getting up and saying soil is the foundation of everything. I used to say it myself. It's one of my favourite sayings. So if we looked at that very simplistically, this is how we all tend to view soil, I'm sure, and certainly for most of my life I have viewed it this way, that you have soil at the bottom of this pyramid, and plants, well, they grow in soil, don't they? And then your animals, if you have livestock, they eat those plants that grow in soil. And then when our crops and pastures aren't performing as we'd like, then we want to add something to the soil to fix it. So if this is the construct, if this is the way that we see the world, our farming agricultural world, if our plants aren't performing as we'd like, our crops aren't producing as we'd like, what's the first thing we do? We go and take a soil sample, send it off to the lab, which will analyse the soil and come back with a report that says the soil's lacking in nitrogen, or it's lacking in phosphorus or potassium or sulphur or calcium or magnesium or something, and you have to add that to the soil to fix it. Right? Isn't that the construct that we've all been told? This is how we see the world, and this is how we deal with the issues if we think our plants or our animals aren't performing as we'd like. It's been our go-to. It's like test the soil, see what's missing. But what if soil is not the base of the pyramid of life? Have we been directing our energies to the wrong thing? And when you look at the input costs that we have and how much reliance we have on that model, take a soil test, add something, and then if your plants still have issues with pests or diseases, then you add other things, the insecticides, the fungicides. Is it because we've actually been looking at soil in the wrong way that we've been making those decisions that aren't leading us in the direction where we need to go? And I'm sure all of you in this room would agree that there could be better ways that we could go that are going to be much more productive and profitable for you, and also better for the environment and for the consumers of your food. So that leads us right back to the question, well, what is soil? How many of you think about that out there when you're working with your soil? What is that stuff? If I had a bucket of soil here, what would it have in it? What is it made of? And what makes it work? We haven't got time to go into that today, as to actually discuss what would be in that bucket and what would be the things that would actually make that productive for you as a farmer. So if we look at the definition of soil, we find that it's weathered rock materials of sand, silt and clay. Depending on what kind of soil you have, it's going to probably have had different origins depending where in the world you are. Sometimes it's going to be very sandy, sometimes it's going to be almost pure clay, or it's going to be somewhere in between, and that's what's called your soil texture. But it's not actually soil unless it's been in contact with plant roots. And why are plant roots important? Well, if you go somewhere in the world where there are no plants because the environment is too hostile for plants to grow in, if it's too cold, it's too hot, it's too dry, it's too something, so you could go to the top of a mountain above the tree line where there's no plants growing, and you'll find weathered rock materials, but you won't find any topsoil. You could go to the Sahara Desert where it's too hot for plants to grow, you'll find a whole heap of sand, you won't find any topsoil. And we intuitively kind of know that, But we need to wind back and look the other way. Well, where plants have grown the best over time, that's where most of the topsoil is. So if you look here in the United States, your prairies are have been your best topsoil, because you had good deep soils grown where there was a variety of plants, hundreds of different kinds of ground cover plants, warm season plants, cool season plants that were able to grow at any time of the year that it rained. There was something there that was green, that was actively growing, and very, very deep plant roots that went down in metric terms several metres, building beautiful deep topsoil. If you take those plants away for any length of time, that soil deteriorates, and the longer it goes without plants, the more it deteriorates. So not only do we have to have plant roots there in the past to build what we consider now to be topsoil, but we need to keep plants there to maintain the health of that soil. You cannot have healthy, fertile, productive topsoil without actively growing green plants and their roots. And we need to look at what kinds of roots they are, how deep they are, how many different sorts there are. So if we look at this like to use an illustration, the soil that is sitting there underneath that grass has over hundreds of years probably been actually built by the presence of that grass plant or other grass plants like it in that grassland situation, because green plants are able to photosynthesize. So they're going to capture carbon dioxide from the air, they're going to utilise light energy and water from the soil to transform carbon dioxide, water and light into biochemical energy in the form of glucose mainly. And then that energy can be moved around inside the plant. It can use some of it to build itself, so it can join the carbon atoms that it's produced during photosynthesis, during the production of that glucose, to make cellulose, which is what its leaves are made from, and to produce the starches and things that will be in the grain, and the lignin that's going to be in the roots, and the waxes and the oils, and all of its plant protection compounds that it will use to defend itself from insects and other diseases. So in that process, it is also going to be exuding carbon from its roots to build topsoil. Now you would ask, why would a plant be bothering to do that? Why would it? This photograph here shows you what it looks like when plants are actively exuding carbon from their roots. A lot of crop plants don't actually look like that, and I'm going to explain why, because this is the process that is going to build topsoil and maintain topsoil, and if your plant roots don't look like this, then it's not happening in your crops. Now, what's going on there is that the plant, in order to acquire the minerals and trace elements that it needs from soil, has to feed the biology around its roots. The plant has to have constant exudation of energy, because the things that live in the soil that will make minerals and trace elements available to plants, they are living and they need energy too. They're going to get their energy from the light, that in the same way that plants utilise light, transform it to biochemical energy in the process of photosynthesis. That energy which we also use, we're utilising light energy when we eat plants, or we eat animals that have eaten plants, where basically the plant converted light energy to biochemical energy, and then we consume that energy in the form of food to run our bodies. Well, the microbes that live around plant roots, they also need energy to perform the work of making minerals and trace elements available. So when there's lots of energy coming out of plant roots, you'll see what are called rhizosheaths around the roots, which is a hot spot of microbial activity, and there's lots and lots of life, trillions of different kinds of, trillions in numbers I mean, of microbes, and thousands of different kinds of microbes living in that rhizosheath. The rhizosphere is the area around a plant root, and a rhizosheath is when you have soil sticking around the roots, which is what we want to see for all of our plants. And if we take high magnification, if we look really closely at what's happening inside that rhizosheath, not that one in particular, but just in a healthy rhizosheath, the plant root is to the left and the soil particles are to the right, and what you're seeing in that gap between the plant and the soil are the hyphae of mycorrhizal fungi and trichoderma and all kinds of saprotrophic fungi that are feeding off the sugars that come out of the plant roots, producing sticky substances to hold all that soil around the plant root. And there are also millions of different kinds of, or millions in number I should say, of bacteria and archaea and yeast and all kinds of things living in that environment. So it's a very food-rich, energy-rich, very protected environment because the riser sheath maintains moisture in there, and in that's the factory that actually processes all the things that your plant needs. The plant can also fix all of the nitrogen that it needs in a riser sheath. So it doesn't matter what kind of a plant it is, you don't have to have legumes to fix nitrogen. If your cereals, for example, or whatever it is, have produced riser sheaths, then they will be fixing nitrogen. If we just move back a little bit in slightly lower magnification, this is in a sandy soil in Western Australia where we grow a lot of our wheat. You can't actually see the roots because that's a kind of a close-up of you can see the fungal hyphae holding all the particles together and pulling the soil around plant roots. If we look at this like in a 3D kind of just a graphic of it, the one on your left is compacted soil that doesn't have good aggregates that have been formed by plant roots, and the one on the right is where the soil particles have been pulled together by the glues and gums from the microbes supported by plants to form good aggregates, and therefore lots of pore space in that soil, where water can infiltrate easily, where air can infiltrate easily, and if the roots are going to support microbes that can fix nitrogen, then we have to have lots of atmosphere, lots of air being able to get into that soil. So good soil structure is important for that because the atmosphere is 78% nitrogen, and that's the way plants have obtained their nitrogen for millennia. And if you look around at the green plants, which aren't there at the moment because everything's covered in snow, but in springtime when you do look out and see green plants, most of the ones that you see like along the sides of the road or in people's gardens where they're not using nitrogen, they're green, but no one's putting nitrogen on them. So even the lawn is getting all the nitrogen that it needs from the atmosphere. If we don't have good soil structure, I'm sure you're all aware of what happens, and I saw examples of this yesterday, although what I saw yesterday was covered in snow. But the one on the right, obviously poor soil structure, water lying on the soil surface. It's not able to infiltrate as it is with the one on the left. So if we look in a little bit more detail now as to what is actually going on biochemically inside those riser sheaths, this is a diagram that was drawn by Rudy Garcia, who's within RCS in New Mexico, and there's a lot of detail in there, and I probably don't have time to go into that detail now, but again, this is on my website and you can read all about it there. There's an article called Nitrogen, the Double-Edged Sword, which has this diagram in it. But the green coming down through the centre of that is a fine feeder root, so carbon exudation is more prolific around young, actively growing roots and around young plants, and then the green bits coming off horizontally from that are root hairs, which are too fine for us to see as a general rule with the naked eye. So inside that aggregate you have microaggregates, the orange areas that are formed by bacteria pulling soil particles together. The macroaggregate, the blue areas, formed by fungi. There are fungal hyphae coming out of that plant root which pull all the soil particles together, and so it's basically it's bioengineering. It's bacteria and fungi in the soil utilising energy from the plant to build new topsoil. That's how new topsoil forms, and that's the factory that it forms in. So what is it that we want to see happening inside those riser sheaths and macroaggregates? We want to see the plants forming humus, because this is going to be the holy grail for your soil. Humus has very high cation exchange capacity and very high water holding capacity, and it is the primary builder of soil structure. So this is what is going to make it much easier for crops to grow and for them to be much more resilient in the face of climatic extremes or in the face of biotic stresses from pests and diseases, because they'll be able to obtain all the nutrients and things that they need. Humus is about 60% carbon, 6 to 8% nitrogen, and a little bit of phosphorus and sulphur. Always in those same ratios. It doesn't matter what kind of soil or where in the world it's built, it always has the same ratio of those components. That adds to about 70%. The other 30% are minerals in the soil. So it's formed in situ, and it's an organo-mineral complex that there's a combination of carbon and nitrogen, both of which are fixed biologically. And if nitrogen isn't fixed biologically, then carbon cannot be sequestered in a stable form. So if we add it as inorganic nitrogen, it will actually reverse this process and destabilise the carbon in your soil. So if we look at the humic molecule, it looks something like that. You can just see that, well, basically in its simplest forms, we've just got carbon, oxygen, hydrogen, nitrogen all joined together by microbes. Microbes have created those polymers. The humic polymer is microbial, and the energy for joining those atoms together comes from the plant, comes from photosynthesis. So the more photosynthesis we have and the less chemicals we're using, the more soil we can build, and the more profitable and productive and resilient farming can be, because this is actually the thing that underpins the processes that you need on your farm to support all the things that are going to make it easier for you. The liquid carbon pathway is what I'm describing. As I said, it starts with photosynthesis. We have to have translocation of the carbon compounds formed in the leaves down into the roots. We have to have aggregate formation around the roots and then humification. So there are 4 steps involved in this process, and anything can interrupt those steps at any point along the way. For example, if we use fungicides on our seed or apply them to our plants, we're basically going to disrupt all the things that those fungal hyphae can do in terms of pulling soil particles together and moving things around in the soil. So steps 1 and 2 require the presence of actively grown green plants, and steps 3 and 4 require a diversity of beneficial soil microbes. So this fertile humus-rich topsoil that we would all like to have on our farms is a product. It's a product of photosynthesis and microbial resynthesis, and it's a product that you can, it's something that you can produce in a relatively small amount of time on your farms. Even though soils we know have been there for a long time, we can rebuild topsoil incredibly quickly, and I'll be talking about that after lunch. So it's photosynthesis, not soil, that forms the base of the pyramid of life. So our pyramid looks like this. We have photosynthesis on the bottom, which requires green plants, light, carbon dioxide and water, the basic ingredients. Roots and their associated microbes. If we were out in the field, we'd be looking at the roots. How deep are they? How vigorous are they? Do they have riser sheaths? How many different kinds of roots are there? And when we get a great diversity there and everything functioning effectively, then we can build topsoil. And as I said, we can build it quite rapidly. So that word photosynthesis basically means photo means light, synthesis is putting together. So the word means making life from light. And it's a very, very powerful thing that you can implement on your farm with cover crops and diverse cover crops, for example, to quite rapidly build topsoil. But you also have to be aware of the things that interrupt that process, because you can have cover crops and still not build soil if you're interrupting the process with high analysis chemicals. So if we just look historically at what's happened on the major continents over time since European settlement, this is a diagram that was presented to the Food and Agriculture Conference in Rome last year, not by me, but it's in one of their publications. And you see there on the left we have healthy soil as it was when the prairies were intact, as it was when our native grasslands were intact in Australia, and the grasslands, the savannas were intact in southern Africa, etc., etc., and the pampas grasslands in Argentina. It's not just the United States, it's around the world. We have seen this change from where the ecosystem was healthy, was functioning, was building topsoil and maintaining topsoil, and then the next frame, as you go to the right, it says at the bottom NPP decrease. That's net primary production. That means there's less biomass on the soil surface. How did we get less biomass on the soil surface? Well, we either overgrazed it, or we burned it, or we ploughed it, or we sprayed it out, or we've got all these amazing ways that we keep getting rid of biomass. We don't want plants, for whatever reason, to grow there. We think it looks great if it's bare. I don't know where that came from, but what we haven't thought about is that if you have a decrease in the amount of net primary production compared to what it was prior to European settlement, then the next frame is SOC decrease. That's soil organic carbon. If you have less things growing on the soil surface, you will have less carbon in the soil. And when you have less carbon in the soil, that takes you to the fourth frame, which is soil moisture decrease, which is probably not such a huge issue in Ohio from what I can gather. You'd probably like it to be, for it to be going off up into the atmosphere and evapotranspiration to be increasing, as that figure shows. But in most other parts of the world, and in fact most other parts of the United States, water is the limiting factor for production, and people would really be preferring to keep more moisture in your soil. But probably the big issue for you here in Ohio is we go back to the third frame, which is soil organic carbon decrease, because if your organic carbon is going down, you're going to have compaction issues, you're going to have water laying on the surface of the soil, and you're going to have all kinds of pests and diseases issues as well, because it's carbon that is actually going to drive the system, and anything that's going to reduce that is not a good thing. In some parts of the United States we get the heat dome effect, where we have that kind of environment. If you look at the fourth frame there, where you've got all that massive amount of heat rising from the surface, actually increases temperature regionally. Jonathan Cobb, who I stayed with last week in Texas, has measured on a day when the ambient temperature was 105 degrees, the soil surface of a bare field was 155. So what that means is that you have air that's 105 degrees, it's heating up on that bare soil surface and rising because hot air rises. Then the other air at 105 comes in and heats to 155 and rises. More air comes in, heats up. You're actually generating heat and creating a heat dome. Under a warm season multi-species cover, the soil surface was 77 degrees. But even if you had brown plants there, like even if you had some kind of crop residues or something that was covering the soil surface and maintaining the ambient temperature at 105 degrees, you're not going to get a heat dome effect. But when you've got bare soil and you've got hot air rising, heating up and rising, and they are on black soils there, it definitely creates a heat dome. We have heat dome effects in Australia, and that's what's happening to us right at the moment. That's why it was 120 degrees in Australia recently. We've had a massive heat wave because we have lots and lots of bare ground that we did not have before. So the presence of green plants is the most important factor for climatic stability, but it's also the most important factor for soil health. How long have I got, Randall? 5 minutes. Oh my goodness. Okay. Just very, very quickly, that's a drought year in Australia. There's crop failure there except for where there was a fence. That farmer has been no-till for 30 years. There's been no soil disturbance. It was a grassland prior to that, never ever been opened up. But we have wheat there for 5 months of the year, and then over the hot months, 7 hot months of summer, bare ground, maintained with a chemical fallow. He's done that for 30 years. This year he just took the fence line out. The fence had weeds growing along it that were capable of responding to rainfall at any time of the year, so there was always something green. There was a big diversity of plants there. There is a huge difference in that soil. Never been cultivated, but where there's been plants growing year-round compared to where there's only been plants for 5 months of the year, look at the difference in the growth. That crop that is growing where the fence line was is not showing any indications of moisture stress. So we have actually created a lot of the issues that we're seeing with our soil by having it bare for a long period of the time. So it's because these actively grown green plants actually support the microbes. It's the microbes that are important, and I'll talk about that this afternoon, that create this well-structured, friable topsoil that we want. So photosynthesis and plant root exudates are now recognised scientifically in international peer-reviewed journals as constituting the primary pathway for soil building. So why is this liquid carbon different to what we call organic matter? Why is it different to returning crop residues to the soil or adding manure to the soil or something else that is actually organic matter? What's the difference between liquid carbon? Well, there's 2 pathways for carbon in the soil, and there's the well-known decomposition pathway where you have something that starts off as biomass like residues or plant roots or animal manures, and then there's the liquid carbon pathway where we have active carbon exuding from roots of green plants. The decomposition pathway still starts with photosynthesis and biomass production, but then all of that material decomposes and goes back to being CO2, or nearly all of it, probably around 98% of it. If you see things like this in the soil, that's a really good sign. That's saprotrophic fungi that are breaking down organic matter, and that's fungal mycelium. That's great. I mean, I'm not saying this process is not good for soil. If you see that, it's fantastic. And we know mulch is great. Decomposing organic matter helps to buffer soil temperatures and maintain moisture, but the soil on the left, that's just decomposing organic matter, will go to be the soil on the right. It cannot stay as it is because decomposition is an active process. It's a catabolic process of breaking things down. The microbes that are involved in decomposition keep on decomposing until there's nothing left there. The other process, the liquid carbon pathway, is an anabolic process, a building up process. It's where very simple carbon compounds come out of plant roots and are polymerised by microbes into complex carbon compounds such as humus, which are very stable in the soil. And if we put those 2 pathways together, you'll see there's a plant in the middle there And the direct line that's coming down from underneath that is plant root exudates that are leading down to stable soil carbon at the bottom. Over on the left, you'll see there's some leaf litter, and then there's root litter as well that often have lignin, sometimes cellulose, hemicellulose, complex carbon compounds, that the microbes that are involved in breaking those things down do produce metabolites, particularly fungal metabolites, that are important to feeding into the humification process as well. So both of those pathways are important, but the liquid carbon pathway is the primary pathway. We now know that plant root inputs can build soil carbon 5 to 30 times faster than carbon derived from above ground biomass. So when we see people producing huge amounts of soil carbon in a very short amount of time, it doesn't fit the standard model that's related to organic matter. So people will say, well, if you add this many tonnes of organic matter, you're only going to end up with this much left in the soil. So how could you build this much soil carbon? There's disputes raging all of the time about, well, you know, how did Gabe Brown, for example, build all that soil carbon? Because you'd have to add so many tonnes of organic matter that it wouldn't be possible. Well, he's not building it through the decomposition pathway. He's building it through the liquid carbon pathway. And that then answers that problem because it can be 30 times faster. And soil organic carbon is that one single measurable factor that tells us most about soil health. I think I'm probably right out of time now. So I'm just going to skip over these. And just tell you that just this one, statistics show that 50% of the world's cropland is bare in any 12-month period. Actually, I just need to go back. 30% of the world's cropland has been abandoned in the last 40 years due to soil decline, and it continues to be abandoned at the rate of 25 million acres a year. And that's all, again, from international peer-reviewed scientific journals. And why? Well, because it's bare. So it doesn't matter what, you know, cultivated or zero-tilled. If there's no green plants there, then you're still not going to be building soil carbon. So I think I'm going to have to leave it there.
Wow, and we're nearly out of time ourselves. That was a lot to take in. I know, she speaks very quickly. But the gist of the matter was that when we look at our agricultural systems, and we look at our soils, what do we do? What do we do that we don't see there? First of all, just, you know, having that mind shift of the bottom of the pyramid is not soil, plants, animals. It's actually photosynthesis. When we think of photosynthesis and we think of the sun, we can't quite wrap our head around putting that at the bottom of the pyramid because the sun is up in the sky. So it really is, you know, fun to start thinking about these things differently. Photosynthesis at the bottom, roots and the associated microbes, and then soils. Soils don't come from nothing. Soils are formed through that process. And that we degrade our soils when we when we leave them bare. And what do we do in Africa most of the time before planting? We clear the land and leave it all bare. So we inadvertently take our soils backwards in order to produce food going forwards, but then we depend on our fertilizers and our systems to support those plants that are growing badly. And that's what ends up in the food chain. Joshua, your hand is up. Come up, come down. Hey, Joshua, I think you've got your microphone now. We can't hear you. Does anybody else have a question or anything that they would like to add, or any comments? Any comments about what we've learned today? We've got a couple of minutes before we actually are going to close. I'll wait for Joshua to get his microphone. And I'm going to come to these questions here. So Wesley has said, seeing the arguments on or of biochar, can we say our traditional ways of slash and burn agriculture and their benefits are useful to soil health? You know, we did a bunch of different things when we did slash and burn, and we also did fallow. We also left plants. So we did a lot of different things. We also didn't have, when we did the burn, we didn't have the highly so-called productive plants that we have today that had so much residues, okay? We did see benefits, but often there was a combination of many things that were at play there. Can we say that waste from plants are best to be used by composting them, I guess, than for fertilizers? When we go on a little bit more about the process of making compost and what actually happens, you'll see that it can actually be used for both. So you can use plant material as a mulch, as something that is slowly going to decompose, and you can use compost to regenerate the soil microbiome and also to add what we call the secondary metabolites, which are the nutrients that are broken down by those organisms in the mix that get into the soils or into the plants, or you can actually put them out as liquid extracts when we utilize our compost. Comment on the use of herbicides to soil health. Well, most of the herbicides kill the microbiomes. So most of the herbicides are put out there to kill the plants. Think about it. What have we just learned? That soil health and the liquid carbon pathway is dependent on photosynthesizing plants. When we bring in herbicides and we quickly get rid of all of that. So herbicides, for those of you who may be in this call that don't know that, are chemicals that we will spray onto plants that will stop photosynthesis and dry the plants up straight away. Well, when that happens, there's no more liquid carbon pathway and no more feeding of the microbiome in the soil. So you're inadvertently pushing your soils backwards by using herbicides. What else has been said there? 1 second, Vivian, let me get through some of these questions here. What do we say about borrowing from ancient farming systems on how they can help us now? I think that a lot of the regenerative process is borrowing from that, and you will hear in our discussion with Dr. James White, you'll actually hear him talking about endophytes, and those are the microbes that get into the plants, and being able to, those endophytes can actually affect the new plants they're going into, can affect them at a cellular level, can almost affect the entire genetics of the plants and the epigenetics of the plants. So that's going to be interesting. We'll learn about that from Dr. James White. Upon watching the video, should we conclude that the introduction of chemical fertilizer to Africans was a scam? I'm not going to say it's a scam. A scam would seem that somebody has got an ulterior motive. It's business. It's not even just to Africa or to Africans. Globally, chemical fertilizers are business. That entire chemical input system is business. It drives big business. And if you go back in time, and if you look up Dr. Vandana Shiva, some of her talks, and she'll remind us that the first chemicals that were used were actually leftover materials from the bombs that were made, the nitrogen from the bombs. And then there was a situation where it became clever thinking that nitrogen from the bombs could go straight in to produce food. And in fact, the gentleman who came up with that theory even won a Nobel Prize, a food prize. So lots of stuff historically that has led to this kind of thinking. And it's only now, after this many years, that we're seeing failed food systems, failed health across all systems, soils, plants, animals, and us. Muthui, you've said some key takeaways for me. The loss of human beings can be directly linked to the soil. That's because of the poor food choices leading to poor health. Absolutely correct. Eric, your aha moment. Organic matter does not have a long-term effect as compared to the liquid carbon pathway, which banks on plant soil exudates and microbial synthesis. Absolutely correct. So when we start thinking about, back to those videos we've watched today, drawing down that carbon, we want to be doing it through the liquid carbon pathway, because that's going to be the pathway that is embedding it into the ground, into the systems that create health for us, because they're feeding the microbes. How can we measure food nutrient density, Wanjiru? Let's wait for that with Dan Kitteridge. He comes and he joins us later on as a guest speaker. He will blow your mind. So I'm going to leave that on the shelf. Should we then go slow on reading? Well, what are weeds telling us? Weeds are telling us a story about our soils, and we'll learn about that along the way. Vivian, the links to the videos and everything, that may have been why your hand is up. It's all in your Canvas class. So make sure that you've linked into Canvas. That's where all the videos are being hosted. We won't be sharing them into the groups. We want you to go to the class where you've got your tests, where you've got your all that information. And we've come to the end of today's class. I don't see anybody else with a hand up. We're going to put microphones on and end our class like we always do. Microphones and cameras, and take me off the spotlight. And if you've enjoyed today's class, I would like to see you come in, put a thumbs up when you're saying goodnight. Say goodnight to everybody, put your cameras on, tell us what you think, and goodbye, everyone, and we'll see you all next week. Don't forget to do your homework. Lovely seeing you all.
Thank you so much.
Thank you.
Bye, everyone.
Good
Night.
night.
Dream about soils.
Bye.
Bye. Bye, Jasmine. Bye, Wanjiru.
Bye. Bye,
Bye,
Sue.
Maureen. Bye, Vinay. Mali. Abisai. We see you. Bye-bye.
Bye. Bye-bye.
I believe you.